In the last video, we explored how to recognize amine functional groups and amide functional groups. We also learned how to classify amines as primary, secondary, or tertiary based on the number of bonds directly connecting the nitrogen atom to other carbon atoms. In this video, we focus on a group of molecules referred to as heterocyclic amines. What you see here is a picture of a poppy seed capsule that is broken open, releasing the poppy seeds. The reason why this is relevant is because of the fact that poppy seeds contain morphine and are the natural source of morphine. And morphine is an example of a molecule that contains a heterocyclic amine functional group. By the end of this video, you will be able to recognize the importance of heterocyclic amine functional groups and a variety of different molecules that have unique biological activities, such as serving as potent painkillers, as is the case of morphine. Let's go ahead and take a look at the types of heterocyclic amines that you may encounter. Here we'll take a look at some common heterocyclic amine scaffolds. What I mean by scaffold is the scaffold is a simple unit that is decorated with other functional groups or alkyl chains or additional rings to construct the final molecule. Heterocycles generally come in two primary sizes. Those are 5 atoms and 6 atoms. The reason why 5 and 6 atom heterocycles are most common is because putting these atoms into 5-membered and 6-membered rings allows them to have as close as possible to their ideal sp3 bond geometry of a tetrahedron. If the ring is made smaller or larger, then the bonds start to deviate from their ideal 109.5 degree bond angle to a greater extent, making the molecule less stable and less favorable to form. So let's take a look at the 5-atom ring heterocycles first. And in each of these cases, in order for them to be called a heterocyclic amine, that is going to indicate that there is a nitrogen as one of the 5 atoms within the ring. For example, if we have a nitrogen with 5 atoms like so, and a hydrogen here to fill the complete octet, we refer to this as a pyrrolidine. I will go ahead and write that out, pyrrolidine. And you should be able to apply this terminology toward problems and recognize when you see this term what we are referring to and recognize this group within a more complex structure. If we have a similar group, but rather than having a 5-membered ring that's fully saturated with hydrogens, instead we have some unsaturation here with the double bonds. Instead, the group is referred to as a pyrrole. Finally, imidazole is another common motif that we see, or a common scaffold, as you might call it. It has, like the others, 5 atoms in the ring. And in the case of imidazole, what we see is that there are not 1, but 2 nitrogen atoms within the ring. And the structure is like so. So these are our 3 common 5-atom heterocycles. We can also look at 6-atom heterocyclic amines as being common and important as well. So taking a look at these heterocyclic amines that have 6 carbon atoms in total in the ring. And by the way, 6 atoms in the ring is generally even more favorable than 5 because it puts the bonds even closer to the ideal 109.5 degree bond angle. So if we have a 6-atom fully saturated ring, that would be analogous to pyrrolidine up there in the 5-atom heterocyclic amines. That was the saturated flavor of that. This structure that we see here with 6 atoms in the ring and fully saturated with hydrogens is referred to as pyridine. P-I-P-E-R, like Piper, I-D-I-N-E as the spelling for that. Pyridine is a 6-atom heterocyclic amine where we have 1 nitrogen atom in the ring and a pattern of alternating double bonds and single bonds. So it's essentially benzene, where one of the carbon atoms has been replaced with a nitrogen. That has important implications for the biological functions of this molecule. And this structure is called pyridine. Pyrimidine is a 6-atom aromatic molecule, meaning alternating double bonds and single bonds all the way around the ring. And it has 2 nitrogens in the ring here and here, and they have to be oriented like so relative to where the pattern is nitrogen, carbon, nitrogen in order for it to be classified as pyrimidine. So I'll go ahead and write down pyrimidine for us. And then finally, purine is a bicycle, meaning 2 rings. One of the rings matches that structure of pyrimidine that we just looked at, so I'll go ahead and draw that in as we saw it before with our aromatic ring, alternating pattern of single bonds and double bonds, and then it's fused to a second ring. This is a 5-atom ring that has a nitrogen double bonded here to a carbon and then an NH group right here, making this structure of this 5-carbon ring here fused to a 6-carbon ring here. That combination altogether is referred to as a purine. And the term purine and pyrimidine might seem somewhat familiar to you if you've taken general biology, because purines and pyrimidines are the building blocks of DNA. And as such, amine groups play an essential role in life, with these 2 structures being the 2 primary building blocks that are assembled together to ultimately form DNA. Now, I need to make you aware of a couple of additional classification terms that you may come across when it comes to these heterocyclic amines. They can further be classified as either being heterocyclic aromatic or heterocyclic aliphatic. So we can classify them as aliphatic if they do not have the alternating pattern of single bond, double bond. In other words, the ring is fully saturated. So they're referred to as aliphatic molecules if the ring is fully saturated. And remember that we learned previously that fully saturated means that we've maxed out the number of hydrogen atoms on each carbon by not having carbon-carbon double bonds or carbon-nitrogen double bonds. On the other hand, aromatic heterocyclic amines will instead have the nitrogen as part of an aromatic ring where we have alternating pattern of single bond and double bonds within the ring. So I'm going to put single double bond pattern as we go around the ring. And with this information, we should be able to classify each of the structures that we've drawn here as either aliphatic or aromatic. I'm going to call those ali for aliphatic or aro for aromatic. Pyrrolidine, starting in the upper left corner, would be classified as an aliphatic because of the fact that there are no double bonds in here. This is a fully saturated ring. Pyrrole, on the other hand, with the 2 carbon-carbon double bonds here and here, would be classified as an aromatic molecule. Imidazole, also aromatic because it is not completely saturated with the maxed out number of hydrogen atoms due to the fact there's a couple of double bonds in here. Puridine, aliphatic. Pyridine, aromatic because of that pattern of double bonds. Pyrimidine, aromatic. And purine, aromatic. And it is no coincidence that the 2 of these heterocycles that form DNA building blocks are both aromatic, because what's been found is that aromatic molecules are extremely stable, even more stable than we would predict from the structures that were analogous but were not aromatic. Aromaticity, the pattern of having these double bonds rather than saturation, confers extra stability on the molecule. And that's important when thinking about the building blocks of DNA, because it's important that the genetic code be carried in a stable manner from one generation to the next. And the incorporation of these aromatic molecules pretty brilliantly does that, because these are very stable and hence can be readily shared and transmitted and passed on. Now that we have looked at the different motifs of heterocyclic amines, we can take a look at an example problem of morphine. Where morphine has, we will notice, 1 amine functional group present. That is signified by our nitrogen atom right here, and the nitrogen is not directly connected to a carbonyl, therefore we classify it as an amine. We can more specifically classify it as a tertiary amine because the nitrogen has 3 direct bonds to carbon atoms. So I classify it as a tertiary amine. And then taking a look at the specific structure of this, what you will notice is that the nitrogen atom is part of a ring. The ring system will be a little bit difficult to identify, I recognize. It's shown with these bold bonds here, forming this ring that is actually fused upon a 6-membered ring here, a 5-membered ring here, a 6-membered ring right through here, and an aromatic ring up here. But what we're focusing on is the amine portion of the molecule, which would be part of this ring here that has a grand total of 6 carbon atoms in that ring. Or I should say 5 carbon atoms and 1 nitrogen to make the total of 6. So here we have 6 atoms in total, like so. And we looked previously at our chart of different amine names with 5 and 6 carbon atoms in the heterocycle, and the structure that this would match from that information we were just talking about, with 6 carbon atom nitrogen atoms making up the ring in total and being fully saturated or aliphatic, is we would describe this group as a pyridine group. And much like I've done here, you should be able to look at a variety of different opioids and other molecules that have heterocycles and specify what of those building blocks that we looked at of the heterocyclic amine scaffolds are present within each structure. Let's do one more example of that. Now, the structure you see here is that of nicotine. Nicotine being the stimulant compound found within cigarettes and other tobacco products. Nicotine actually has 2 different heterocycles present in it. So let's take a look and identify each of those. The heterocycle at the left is a heterocyclic aromatic compound, or heterocyclic aromatic group, I should say, with 6 atoms in total in that aromatic ring. That would enable that structure to take on the descriptor of being a pyridine based on our earlier information in this video. On the other hand, at the other hemisphere of the molecule, we have a 5-atom ring in total, and that's fully saturated, so we describe that as an aliphatic group. And that aliphatic heterocyclic amine we would describe as pyrrolidine. So I'm going to go ahead and write pyrrolidine and give myself a little spelling test here to see if I get the spelling right of pyrrolidine, the 5-atom ring that we see here, which we describe as aliphatic because it is fully saturated with hydrogen atoms. There's no double bonds. Whereas pyridine we would describe as an aromatic group because of that presence of double bonds and unsaturation within the ring. So now that we've done this video, you should be able to take whatever type of structure I give you and evaluate it for the presence or absence of the different heterocyclic amines that we have evaluated here.